Constant focal length scanning is a concept that we came up with in order to ensure that the beam properties all across the wafer are constant. The idea is to scan the beam, scan the wafer in the plane of the tilt. So if we run a 7-degree tilt, we scan the wafer at 7 degrees. That gives us a constant scan velocity, scale to the beam current, that we don't have to scale to tilt angle in order to get the right dose. And it ensures that the beam shape and beam size from top to bottom of the wafer is constant. The parallelizing lens, or we call it the P-lens, is an electrostatic gap that accelerates the beam after extraction and scanning to create a parallel beam. We scan the beam in the horizontal plane to span the wafer, in this case a 300 millimeter wafer, and the beam after scanning passes through the P-lens, which is a curved lens, roughly parabolic in shape, that cancels the scan angle to create parallel rays following the P-lens. The basic shape is parabolic. There are also shapes in the vertical plane and in the gap that control vertical focusing of the beam, so that the beam comes to a vertical waist down the acceleration tube all at the same point, regardless of the scan distance. The P-lens ensures that we have constant angles at all points across the wafer, and is very precise in doing that. The beam line is designed to eliminate contaminants in two ways at least. We start with the analyzing magnet, or the AMU magnet, that selects a specific species from the source and ensures that we're only projecting one species through the rest of the system. After we scan the beam and accelerate to the final energy, we analyze the beam electrostatically with a vertical deflection in our region called the angular energy filter, or AEF. That gives us the ability to eliminate any energy contaminants that are created after mass analysis. So when we decelerate the beam, and we use this technique to achieve higher beam currents at low energies, we use high deceleration ratios. And in general, that might lead to a contaminant. But the only contaminant in that case is the ions, energetic ions, going to neutral before they've reached the final low energy, for instance. And the AEF bend ensures that those ions can't make it to the wafer. So both for low energies and for multiple charge species, the AEF is instrumental in eliminating any possible energy contaminants, and ensures that we implant one species and a pure energy. One of the things we've done on this tool is to try to improve low energy beam currents, and we have electrostatic deflection of the beam, as I mentioned, in the angular energy filter region, which strips the beam of any neutralizing electrons that might otherwise accumulate in the beam. But we can compensate for that by raising the energy in these field stripped regions. And we do that by never letting the beam reach its final energy until it's completing the bend in the AEF. So we decelerate through the acceleration column only to a limited amount, because we run then electrodes higher in voltage, higher negative potentials, so the beam energy stays elevated by, say, 10 kilovolts through that region. And then as we complete the bend, it's dropping to its final energy, and still gives us the ability to deflect beams, maintain good energy purity, and higher currents at low energies. The tool has a wide energy range from near 1 keV to 335 keV. We've achieved the low energies, as I mentioned, by using biased components after our final decel to keep the beam energy up and improve transport. We've achieved the higher energy of 335 keV by designing for the terminal to withstand these high gradients to the grounded enclosure. And if you look at the terminal, you'll see large radii, particularly on the corners of the terminal, and these were shaped to tolerate the fields that would be created at 275 to 300 kilovolts on the terminal. And that lets us achieve up to an MeV with triple charge ions. Our in-situ angle control is very important to today's products that are being made. Angle control is a key issue to halo implants and many other conditions where it's important to get into the right place on the device. We measure horizontal angles with a mask and a traveling profiler at 7 points across the scan beam. And this can be measured very accurately to 1/10 of a degree. The vertical angle is measured with a channeling type mask on the back of the chuck. And so we make that measurement both of those measurements just prior to starting the implant. And the vertical angle can be corrected by tilting the wafer by whatever angle that error finds. And the horizontal angles are corrected by adjusting the P-lens voltage and the horizontal position with a steerer. So this all happens automatically at the start of an implant and ensures that the angle called for in the recipe is the one that you implant. Photoresist outgassing is always a problem for ion implantation dose control. The outgassing of the photoresist causes high pressure in the end station. This creates neutral ions as the beam passes through it. Our dosimetry system doesn't measure neutral currents, and so you end up dosing partially with current that you can't measure. We've come up with a scheme to handle that by using 2 Faraday cups to measure the current during the implant. One is more forward of the wafer than the other, and the fact that they are in different distances from the wafer means the beam passes through more gas to get to one of these cups than it does through the other one. So the one cup that's further down the beam line sees more neutrals, i.e. a different current, than the cup that's further up the beam line, and that difference in current can actually be used to derive the neutral current created between those 2 cups. And with a little more arithmetic, with things that we know from the geometry of the system, we can actually calculate the neutral flux from these 2 cup currents without using pressure compensation. That's how we control photoresist outgassing dosimetry.